Now, whenever we look at the Young's modulus, this is the picture that should come to your mind. So here is the metal rod. We are stretching it from both sides, that is, we are applying stress, and then because of which strain is developed, and that means the length of the metal bar, it changes, and finally it develops a neck and then breaks. Now, that is the case for the ductile materials such as our metal here, aluminum, steel, those are ductile materials. And this is the stress strain curve for the ductile materials. There is a clear regions that we can find here. That is the Hooke's law region, the elastic behavior region, okay, all the way from O to B. And then after B, there is this plastic behavior region. And finally, there is necking starting from D, and the breaking or the fracture point, which is the E. Okay, so that is the case for the ductile materials, and that is the stress strain curve that we are used to seeing. What happens if I use brittle materials such as glass? What kind of stress strain curve would I get then? Okay, in the case of brittle materials like the glass, what happens is that for the same amount of stress, okay, so I am applying the same amount of stress, the change in length is actually very small, and that is to be expected. The glass, if I apply the stress, it does not change in length very much. Okay, and after a while, the brittle material would just break, it would just fracture. If I continue to apply the stress, then it would just fracture. It would never enter the plastic region of the curve. So ductile material, it enters the plastic region of the curve, and that is not the case for the brittle material. So brittle material, it never enters the plastic region of the curve, and it simply breaks. So this would just be the point of fracture. So there is a linear region, of course, where the stress is proportional to the strain. As soon as that region ends, the brittle material would just fracture. It would just break. That is to be expected, right? You cannot be expected to bend the glass, for example. Okay, if you try to bend it, it would quickly break. It would just not take the strain very much. It would not change in length very much. You continue to apply the stress, and finally it would break. So the strain is also that not very much, which means that this line, it becomes steep, because for the same amount of stress, right here, rise, there is very little run. Okay, so this curve is very steep for brittle material, and then there is no plastic region. There is simply fracture after the linear stress proportional to strain region. What about the plastic material? For the plastic material, the curve is other way around. What happens is that there is a very small linear region where stress is actually proportional to strain. After that, for the case of plastic material, if I continue to apply the stress, then for very little change in stress, my strain actually changes by a whole lot. That is to be expected again for the plastic material, because the plastic material would just bend, because it would just bend, right? So there is a lot of strain, there is a lot of change in delta L for very small change in my stress. So this is the plastic material. It enters the plastic region very quickly. There is very small stress being proportional to strain region right here. Elastic region is very small. Okay, after that it enters the plastic region where there is permanent deformation, and in that plastic region, for very small stress, I am able to produce a large amount of strain. Okay, so hopefully this is very clear. Qualitative questions, okay, based on your experience with materials, are asked on this topic. Very scoring again, provided you know these curves, okay, especially which of these curves is steeper. So brittle is steeper than ductile, and ductile curve is steeper than the curve for the plastic material. Okay, thank you.